Drawing Lewis structures is a critical skill for success in organic chemistry. First, let's review what a Lewis structure is. Lewis structure is a drawing of a molecule showing the connectivity of all of the atoms and the location of all of the electrons, whether they're in bonds or in lone pairs. Okay, so a typical problem that we would have to be able to solve is given a molecular formula to be able to draw a correct Lewis structure for that formula. And we're going to start with a very simple example molecule with the formula C2H6O. Okay, so the rigorous solution of how to solve this problem is to start by determining the total number of valence electrons for the molecule. Okay, so to do that, we consider the elements in our formula, in this case carbon, hydrogen, and oxygen, how many of each element there is. Okay, so there are 2 carbons, 6 hydrogens, and 1 oxygen. The number of valence electrons that each of those elements contributes, followed by, when you multiply together columns 2 and 3, we get the total number of valence electrons that you get from that element. So for carbon, 2 carbons, 4 valence electrons, 8 valence electrons total. Hydrogen, there are 6 of them. Each one contributes 1, so there's 6 of those. And oxygen, there's 1 oxygen, but it contributes 6 valence electrons, so that gives us 6. Add them all together, you get a total of 20. Okay, step 2 is to use as many of those 20 electrons as possible to form chemical bonds between atoms. And you have a greater chance of success if you put atoms that form more bonds closer to the center of your structure. But as we see, that's not always going to be true. So let's try to go ahead and do this. Let's try to come up with a reasonable structure. And following this principle, we will put a carbon atom at the center. And that carbon atom is going to have to form 4 bonds. So I will draw 4 bonds to the carbon atom. So what else? We have another carbon atom. So let's bond that other carbon atom to our initial carbon atom. It is also going to have to form 4 bonds. So I need 3 more bonds to that carbon. And then my oxygen's got to go somewhere. Well, let's just, for the sake of argument, put it on the right side. Although I could have just as easily put it on the left, and we would have ended up with the same structure. Okay, the oxygen's got 1 bond. It's going to need 2 bonds. So we will go ahead and draw another bond to it. We've used our 2 carbons. We've used our oxygen. Now we have 6 hydrogens left. And luckily, we have 6 places that need another atom. So we're just going to put a hydrogen in each of those 6 places. And then that gives us a correct structure. Okay, step 3 is to assign all the remaining electrons as lone pairs on atoms so that each atom obeys the octet rule. Okay, so in the structure that we drew down here, we have formed 1, 2, 3, 4, 5, 6, 7, 8 bonds. So that means we have used 16 of our 20 valence electrons. In order to use all 20 valence electrons and ensure that the oxygen obeys the octet rule, we need to put 2 lone pairs on the oxygen atom. This is a common organic molecule called ethyl alcohol, one that some of you may be quite familiar with in a more recreational setting. So step 4 is to check your work. You can always check your work in these problems, because just look at the atoms, say, is each atom forming the correct number of bonds? Check. And do you have the proper number of valence electrons in your structure? Do we have 20 of them total? Yes. Good. Now, this is the rigorous way, but I would also like to point out a shortcut, because you're frequently not going to have enough time when solving a problem, especially on an exam situation, to calculate the total number of valence electrons and go through this algorithm step by step. So if you remember the following, you'll be able to solve these problems faster. Hydrogen gets 1 bond. Carbon gets 4 bonds. Oxygen gets 2 bonds and 2 lone pairs. Nitrogen gets 3 bonds and 1 lone pair. This now begs the question, was the structure that we drew the only possible structure you can draw with formula C2H6O? And the answer to that is no, because I could have also drawn this structure. Okay, this one has the oxygen in the middle, in between the 2 carbons. If you look at this structure, everything is good about it. Your carbons are forming 4 bonds, your oxygens have 2 bonds and 2 lone pairs, your hydrogens have 1 bond, and you still have a total of 20 valence electrons. This molecule is called dimethyl ether. Okay, may not be quite as familiar as ethyl alcohol, but it is also a legitimate organic molecule. So this brings us to the concept of isomers. We have clearly drawn 2 different molecules out of the same molecular formula, and whenever you have different molecules coming from the same formula, you have isomers. So one way that we know that these particular molecules are different is that they have different physical properties. Physical properties will be detailed in a different lesson, but for the moment we can just look at boiling points. Ethyl alcohol is a liquid at room temperature with a boiling point of 78 degrees Celsius, and dimethyl ether is a gas at room temperature with a boiling point of -25 degrees Celsius. These molecules are specifically called structural, or in some books, constitutional isomers, because they have different atomic connectivities. Later on in this course, we're going to talk about more subtle types of isomerism, so that's why I want to introduce from the very beginning that the correct term for this is not just isomers, but structural or constitutional isomers. And if you look for more isomers with this formula, you're not going to find any, because you can't come up with any other structures without violating the rules for how many bonds an atom can form. But as molecules get larger, there will be more isomers available. So let's look at a more difficult example. Instead of C2H6O, let's look at C3H6O. And let's see what we can come up with. Well, we will start by putting a carbon in the center. Let's bond another carbon to it. And now in this case, got to draw all of our bonds to the first carbon, we have a third carbon to contend with. Okay, so each of our carbons is going to have to form 4 bonds, and there's also going to have to be an oxygen there. Well, why don't I stick the oxygen on the right, and let's see what happens. Well, if I've drawn my 4 bonds to the central carbon, I know that the other 2 then are going to have to be hydrogens. And if I go to the left-hand carbon, it's also going to need 3 hydrogens. But I have now used 5 of my 6 hydrogens. I only have 1 more hydrogen left. But I have a carbon that needs 2 more bonds and an oxygen that needs 1 more bond. How can I solve this? I don't have enough hydrogens to give these atoms the number of bonds that they need. Well, this is where we can put in a double bond. Okay, we can put in a carbon-oxygen double bond, and as a result, the carbon is only going to need to form 1 more bond. The oxygen is now happy, it is forming its 2 bonds, and I have used up my 6 hydrogens. Just like in the other examples, the oxygen's forming 2 bonds, so it needs 2 lone pairs, and we're going to put on the 2 lone pairs. Again, there are different isomers that I could have formed with this structure. In addition to a carbon-oxygen double bond, I could have started out knowing that I need a double bond with having a carbon-carbon double bond. Well, now making sure that I don't exceed the number of bonds that carbon can form, I can start adding some hydrogens. I can add my 3rd carbon. And I can add my oxygen, which is also going to need a hydrogen, and 2 lone pairs, and I have come up with another structure with 3 carbons, 6 hydrogens, and 1 oxygen. These are not all of the structures, there are actually even more. So once you get into double bonds, there are a lot more opportunities to come up with a lot of different structures.